the title suggests, are dual to monads. And so I thought it would be a good introduction to see what actually duality means. So suppose we have some construction. And when I think of construction, I think of a collection of types and function signatures between those types that satisfy a certain set of equations between those functions. And the dual of a construction is the collection of function signatures and equations with all the function signatures reversed. So, I mean, this is sort of something a little abstract. So let's start with an example. The typical example is a product versus a sum. So this is your tuple or your either. So as you can see, a product has an int and a string and a tuple, and it has two projection maps, first and second. Whereas either, the arrows are the opposite direction. You have left and right go into an either. But what really characterizes these constructions is this, what is called a universal property. And what that is essentially you take any function that goes from double to int and any function that goes from double to string, you automatically uniquely get a function that goes from double to the tuple of int and string. And if you reverse all the arrows, you get a sum. So anytime you have a function that goes from int to double and then string to double, then there is uniquely a function from either int string to double. This is the product t and sum t functions. And they satisfy these properties right here. So you've noticed this is where the equations get reversed. This sum t, it becomes first, whereas this product t is last in the chain of composition.
What is double?
Double is just like a number, like a floating point number. It's just an example. You could obviously put any type. Yeah?
How is it unique? Can you have some other function in double and replace that in the either case?
So it's uniquely determined by f and g. So it's unique to satisfy. What?
So like given f and g, there's a unique function.
Yes. There's only one function that satisfies this property of commuting with all these different arrows. Yeah. Okay. So, comonads. So basically, what a lot of pure functional programmers really care about is referential transparency. And referential transparency is really reflected by the application operator, which says when you have a function from a to b and an input a, all you get is b, right? But with monadic functions, you're not really outputting data, you're outputting an action on data in a context. And that context is the monad M. And so you don't really apply functions so much as you bind those functions to the context. So monads are functions, monadic functions are always functions that output actions on a context. And in order to satisfy this, the do nothing operation switches from identity to return. Return, since you have this constraint on monads where you always have to output actions on the context, the do nothing is really outputting into that context. It's not just returning the thing. And if you bind identity to some monadic data, then you get the join operation. Now, comonads are sort of the opposite. Functions always take context actions as input. So instead of applying, you always sort of extend your input function over the entire context. And since you always have to satisfy this constraint of taking an input action or a context action as input, you have the do nothing operation switches from identity to extract. So this is sort of a lot of abstract nonsense. I think one thing that might help with the intuition is Comonad, just like Monad, is a subclass of functor. And functors just implement this, this function fmap, which allow you to sort of a generalized map over a list where you have an input function, and then you automatically get the function that applies that function to everything in that container. But fmap, the function that you input only has access to the single item, whereas extend in Comonads has access to the whole structure. So you can think of this as you're computing something local, but that local computation is on the requires some information around it, and then because it requires the whole information around it, it can be extended over the entire context. Yeah.
Can you zoom your screen possibly, because I can't see the formula very well?
Yeah. Oh, 75%? Does that help?
Even more? No change.
Oh, okay. Not usually a Windows user, so.
F11?
Okay. I'll try that. FN F11. Okay, F11. Okay, is that better?
That's better. Do it again. Do it one more.
Control plus. Sorry about that. Well, I guess I'll continue. The slides are on slides.com/nihils. So if you need to follow along on your laptop, then we have that. So Comonad lists are actually a Comonad in at least 3 different ways. You have prefix lists, where the duplicate function gives you the set of all prefixes of that list. And extract will give you the last element of the list. And you need these to satisfy, you need prefix lists to satisfy, to act that way to satisfy the Comonad laws. And suffix lists are a little the opposite, where extract gives you the first element of the list and duplicate gives you all the suffixes. So for example, a prefix list duplicate on 1, 2, 3 will give you the list with list 1, list 1, 2, and list 1, 2, 3. What this is useful for is for any summary statistic you have, sum, mean, median, something more complicated involving signal processing and a stream of data, you automatically get the accumulating version by using this extend on a prefix list. Whereas if you were to use it on a suffix list, you automatically get the dissipating version. Lists are also a Comonad over permutation. So if you have a list, or cyclic rotation is a better way to say it. If you have a list 1, 2, 3, extract gives you the first element, just as in the suffix list, but duplicate gives you sort of all the cyclic rotations of it. So you start with 1, 2, 3, and then you get 2, 3, 1, and then you get 3, 1, 2. Another example of a Comonad is a suffix tree. So a suffix tree is where the extract will give you the data in the top node of your tree, 42, but duplicate will give you the tree of all subtrees. So for example, this green node right here, the subtree that is under it is, well, just itself. Whereas if you have the blue node, right, the subtree is the blue node with its child, the green node. So hopefully it's a little hard to explain in words, but I think this image probably conveys it a lot better. So one example of using a suffix tree is in computing a Merkle tree. So Merkle trees are used a lot now because of Bitcoin, but they've been around for a while. They're also used in Git. And a Merkle tree is essentially just a hash of a tree of hashes, where if you modify some ancestor, then you want some child, then you want the ancestors to all have modified their hashes. There's many different schemes for doing this, and essentially what I do is I map the hash function over all the children and then concatenate that with the hash of the top node and then hash that whole thing. So just sort of using some fold thing. So this computes the hash for that top node in the tree, but if I want it for all the subtrees, then I can just use extend, and then you get the tree of hashes. Another comonad is a store comonad, and a store comonad is sort of similar to a generalized map, as in like a hash map or a dictionary, where you have some function, a key to value mapping. So your keys are S, and your values are of type A, and then you have some point, some cursor, which is represented by a specific key. And extract just applies your key value mapping to that specific cursor key to give you the value at that point. And then duplicate gives you the store of stores. It's a little hard to explain, but of stores where each store has an inner cursor at the cursor in the outer store. So to explain this, I think the image is a lot better. So suppose we have an image of the Mona Lisa. We can put on a grid on it, and our store has keys, the image, and the different rectangles. And then we have the cursor, so the entire store is represented by this full image. The cursor is placed at a specific rectangle. And so to extract, we just apply this getRectangle function to the specific rectangle, and then we get the image region, the value at that point. Duplicate works more like this. So we have the store of stores where each cursor is placed at the position in the inner store of what that position is in the outer store. And the cursor for the big cursor is at the original position. So what this can be useful for is actually doing a lot of blurring and image processing. So if you have a median function, which basically takes all the pixels in a certain region and sets it to the median color value of that region, then you can do something like extend, and then you get the full median blur. But you can do this for any sort of coordinate geometry you want. So if you were to have regions that weren't a square grid but were circles centered around some point, then you'd get radial blurs. You could also do box blurs in this way. So I started with comonads. So what are Cofree comonads? So free monads are sort of a sum of a pure value and a raft value. We can think of free monads as the least monad you can get from a functor. And what that means is sort of you don't really annotate the computation, or you don't really do any sort of monadic computation. You more annotate that you're going to do this computation. One way of thinking of free is that you're wrapping applications of f with leaf values a. So while free monads are a sum of a pure value and a raft value, a Cofree comonad is a product of a pure value and a raft value. And so the way you can think of this is if you have a tree of these nested f's, with each branch you're annotating it with a values. So a lot of the comonads we've discussed now, up until this point, are really Cofree in disguise. they're Cofree Comonads over a different base functor, of some base functor. So the stream is really a Cofree Comonad over the identity functor. So you can see sort of with 1, you have an annotated value, then the identity 2, and then you keep doing this, and it goes on infinitely. That's what a stream is. A prefix list is a Cofree Comonad over the maybe functor. So you have the just 1, just 2, and then when you want to terminate, you get nothing. A tree is actually the Cofree Comonad over the list functor. And I think this illustrates it pretty well. At each nesting, you have a list, but you annotate it with a value, and that annotated value on the list is the actual data in the node of the tree, whereas that list is the children of the tree, of the node. So what this can be useful for in practice is annotating domain-specific languages. So suppose we have an abstract syntax tree that represents some logic formulas, and we just have a base values that are Booleans. So you could represent it as and, not, or, and this is sort of the tree where we're taking the and of not of false, and or true or false, right? And the way the sort of operation I'm going to do the operation as is each step I'm going to convert this abstract syntax tree to a Cofree Comonad on the expression tree type to have an annotation of just unit. Then I'm going to do a Cofree Comonad computation to actually compute at each level the branch value. So if we start with false, and then not of false is true, and if you start with true false, and then the or of true false is true, and then anding two trues gives you a true. So this is the actual code for that process. We have some expression tree which takes some values of type bool, or I made it polymorphic in A, and then you have the ands, ors, and nots on this recursive variable f. And what fix gives you is this sort of arbitrary nesting of expressions. So you can't just have like an expression, and then bool, you can have arbitrary nesting. And then I use unitcf to convert this expression tree into a Cofree Comonad expression with values annotated unit. Then I use this reduce function to recursively apply the actual operation to the bool. You could achieve something like this with a catamorphism, if anybody's familiar with that. But with the catamorphism, you don't get the accumulated values at each branch. And then using extend reduce, that's where you get to sort of accumulated values over the entire tree at each branch. And then you can obviously provide a different interpretation when you're using floats. This is the example for fuzzy logic instead of a classical Boolean logic. So another example of a Cofree Comonad is a Cofree Comonad over a function functor from a fixed type B. So the way you can think of this functor is B in B function 2, and then that blank is where you put the what the functor is going over. And so you can actually Cofree Comonad over this functor is actually a finite state machine, with transition types being the input type of your function functor, and the states being of type A, where you the actual data type of this Cofree Comonad. So I got this finite state machine from an article on designing Ethereum smart contracts, where you're trying to simulate a blind auction. So there are various states in a blind auction. You have a state where you're accepting blinding bids, and then you can keep doing that. So this is this loop bid, and then you close the bid, and that's when you start revealing the bids. But also when you're accepting the blinding bids, you can cancel a bid, and that's when you go to the cancel state, and then you can unbid, and then you loop back that way. Or from after revealing, if you want to cancel, then you go back to the cancel state. And finally, after a certain point, you can go to the finish state, where you get the finish. You're at the finish state, and then you start withdrawing the auction money. So this is how you implement a finite state machine as a Cofree Comonad. This is, remember, a finite state machine, a Cofree Comonad with over the functor with input types B has transitions of type B and states of type A. So recall that the different states that we had in our finite state machine were accepting, revealing, canceled, bid, and finish bid. And the different transition errors were bid, unbid, reveal, close, finish, withdraw, cancel. And so the actual leaf, or the wrapped values, are functions of this form, a transition, or B, action, to another finite state machine. And so basically, since this was a loop, when we hit a bid action, we want to go back to the same transition. So we set the state back to accepting, and then we go to the accepting way of encoding the transitions. And then if we have, say, a cancel transition, then we go to the canceled state. And then we go to the, whoa, my bad. Canceled state, where we then have the handler for the on-canceled transitions, and the same thing for close. And I sort of finished the uncanceled function this way. So when you have a finite state machine, once you filled it out in this fashion to encode all of this, then you can actually do the execution. So suppose you have an accepting bids function, which contacts some things in the outside world and returns an action. Then you can run this finite state machine by taking pattern matching over the different states, and then applying the next action, which is what this F means, to the resulting action that accepting bids is figuring out where that is, and then binding it to execute. So recursively call and keep executing until you reach the finish state, where you don't really care about what the next step is, because you don't want to infinitely loop, and then you get a withdraw bids, and you can do something like this. So just since comonads are dual to monads, pretty much every property you can think of monads have their dual. And so everybody's heard of sort of the monad transformers library, which allows you to stack different contextual effects on top of each other. And one of the things you gain from the monad transformers is a lift function. So return on this stack of monads, state t int io, and your internal monad is the io monad. Returning a text into this monad lifts it all the way to the state t int io, the double stacked monad. Whereas lift takes an io text and lifts it up to the one higher monad. Comonad transformers, since they're dual, you start with extract, which is dual to return, and when you have a store comonad transformer that wraps a suffix list comonad, extracting will give you the last text within the latest or the cursored suffix list in the store. Lower allows you to go lower one level in the store to where that cursor is and give you the suffix list at that cursor. So for example, this is how you would write the Cofree Comonad type. You need this Cofree F to make sure that this B is sort of polymorphic and you're actually getting the W. It's a little interesting that way, but the way you would actually model a type of chain of trees is, if you recall, a Cofree Comonad over the maybe functor is just a linked list, a prefix linked list, and so a chain of trees can be modeled as this type, a Cofree Comonad transformer with base functor maybe and base Comonad tree. So since it's 2018, I should probably talk about blockchains. I'm still skeptical of blockchain as a technology, but I thought it was sort of an interesting way to learn about Cofree Comonads. So a blockchain essentially just has a linked list structure. So as I mentioned probably many times in this talk, a prefix linked list is a Cofree Comonad. And so it sort of trivially fits into this paradigm. A blockchain is just a list of a block header with some transactions. And you link it like this. And so we can model it like this. We have our transaction type or block type with all the header information. And a blockchain is just a prefix list of a block. Now remember, the latest block, extract, gives you sort of the last element of that prefix list. And so it sort of has a nice semantic characterization in that you kind of want to fetch and extract the latest block, and that's just the extract function from the Comonad. And the ancestry of a block, all the things that went into that block's computation or that block's verification, is just the duplicate. So if we have a verify function for verifying a block, you can verify the whole chain by extending it. Now remember, a prefix list is a Cofree Comonad over the maybe functor, and so this is equivalent essentially, or isomorphic. And one way you can think of the nothing in the maybe is as the genesis block. But there's some information in the link. And I think a better way of modeling what's actually going on is the link is really a parent is the hash of the parent, the previous block in the blockchain. And so we want to basically rip it out of the header and put it on these links. And so the way you would modify this with a Cofree Comonad is you'd switch from this maybe as your base functor to your this chain functor as your base functor, where you have your nothing replaced with the genesis block, and then you have each new block be a node with an annotated hash with the parent hash. And you can play this trick where every time you modify the data within the block using an fmap, you automatically rehash the hash associated with the parents. And you have to do this constraint because you want to make sure that the data that you're actually hashing is the data that's actually in the Comonad is actually hashable in order to have this functionality. So you do this little constraint kinds trick where you have to put a type constraint on the actual output values of your fmap. It's sort of a little trick that happens a lot in Haskell. This is how you get fmap to work with data.sets. So then a blockchain would just be a Cofree Comonad with this chain functor as our base functor, and then we have blocks. But the data in a block, we've always modeled as just a list of transactions, but that's actually not how it's always structured. In fact, the Bitcoin blockchain uses a tree of transactions. So it looks something more like this. And a tree is just a comonad. And so we can have, just as we did the chain of trees, we can sort of play the same game here, where we have a Cofree Comonad transformer with a base functor, that chain functor, and a base comonad, the tree of transactions instead of a list of transactions. So what I do is I shove all the things into the link, into the block header, and so I change my chainf type to the block header. And then I have my base comonad as tree, and then the blockchain would be modeled as a Cofree Comonad transformer with base functor chainf and tree as their base functor, and then transaction. So what changes here is extract will give you the latest transaction on the latest block, whereas lower will give you the latest block. With this design, we can have our base comonad be prefix list of transactions, a suffix tree of transactions, or even the base functor could itself be a Cofree comonad with that finite state machine representing a smart contract. Or rather, I think something like Ethereum would actually be the base comonad would be the blockchain, and the finite state machine would be executing state actions. So the finite state machine would be the Cofree Comonad transformer. Or it can be a store representing image regions and movie frames. And I think this is sort of relevant because there seems to be a lot more enthusiasm around blockchain technologies outside of cryptocurrencies. One example of this was the Oxford Internet Institute came out with a paper earlier this year on trying to use blockchain to prove the origins of media content. The idea being that if you could do this, then you could sort of help to verify that you're getting the actual image and the actual video that they say you're getting, and you can check, verify, everybody has consensus that this hasn't been modified. And this is as a way of combating sort of fake news. And so if we have our base comonad be a store, using the store comonad, which stores image regions, we can store image regions on the blockchain and have them verified. So, I don't know if you read this article, but there was an article about an AI technology using to look through the images on movie frames and find the faces in that movie frame and splice Nick Cage on the movie frame. So we can help stop the cage using a Cofree Comonad blockchain with the base comonad being a store. So some takeaways. Comonads are an equally important abstraction as monads. I like to think of them as sort of modeling superdeterminism. So when you have a context-dependent computation on a piece of data that depends on the entire context around it, then you can use extend to extend it over the entire context. Cofree comonads are useful for annotating branches in a tree. That's what we did with interpreting domain-specific language. You can also use it for annotating data with the computed hashes, as I did in the second blockchain example. You can use a Cofree comonad to represent smart contracts, or really represent finite state machines, more machines in particular. And then you can use a Cofree Comonad transformer to create a container-agnostic blockchain. To actually implement some sort of proof of work mechanism into this is sort of an exercise I leave to you. But any questions?
So I think part of this thing is that you get a lot of boilerplate for free because it's like one, we'll start implement this on the virtue of being common.
Mm-hmm.
So you just say, hey, I have a Comonad, and you use a lot of cool stuff.
Yeah, you can use a lot of the categorical things.
So it's like, you're folding easily and you're summing up the transactions maybe. You don't need to write boilerplate for it.
Right. So it reduces the code base, but I also think having it be container agnostic, I think, adds a lot. One thing I should also mention is you have, as you have do notation from monads, you have co-do notation. And with co-do notation, it's unfortunately not a first order language construct in Haskell just yet, but there is a quasi-coder library which you can use co-do notation with, and you can start to write sort of imperative-looking code for extracting data from these comonads and doing modifications. So you can imagine doing a lot of blockchain computations with this. You had a question, Mark? Yeah.
On your finite state machine slide, where you're actually implementing it, is there any way to protect against invalid transitions?
Invalid transitions.
Yeah, so like the accepting bid state can't do a finished transition.
Right, so.
There's like no type protection on it.
Oh, yeah.
So,
Yeah, I see what you mean. Like, this is a partial function
yes.
over action. Yeah, I haven't done the thinking on how to actually do that, but I would, once you have a valid like finite state machine like this, then you'll never, once you actually build that up, you will never actually get to that state when you execute it. So if you build it in the correct way.
So, follow-up question. So monads have the index monad concept, where each monad has initial state and end state.
So,
and the payload, right? And
so
you can bind on if the matches. I wonder if there's an equivalent in the Comonad.
yes. So indexed monads, you basically index your monads with a small parameter, which comes from a monoid.
Okay.
And so, so the join essentially is if you have the monad sub D and the monad wrapping a monad sub D prime on the A, then a join would give you the monad sub D monoid operation D prime A. Does that make sense? So it actually isn't the case that indexing comonads, you don't index them with comonoids, you still index them with technically any monoidal index category. But
I'm asking you the question because maybe that could be relevant to build some sort of validation. Maybe it would be more restricted. Because that's what happens in the monad world, which gets a huge amount of restriction of how you bind.
okay, I see that.
Maybe it's part like that, right?
Mm-hmm.
So,
Index state. Index code state.
yeah, and one of them is possible. Not really
So any,
question?
yeah.
You illustrated very clean programming here. Do you ever feel the need to do some theorem proving to show that a program has a certain property, or maybe that two different implementations give compatible results or something like that? Is there a theorem proving need that might come up?
Yeah, I definitely think so, especially if you want to do something like a blockchain with this. And the nice thing is you can import a lot of some of the results from category theory and use, say, the category theory package in Coq, and you can sort to validate certain things about the computations you're doing using a theorem prover like Coq. And I imagine there would be, if there like $50 million or something is being stored on the blockchain, you'd probably want some strong formal verification on your design, software design. So.
Could you show the URL of your slides?
Yeah, it's on slides.com/nihils, NIHIL S. And there's like a link to this slide, this set of slides, this slides deck.
Can you repeat that?
Can you press F11
Yes.
again?
Just go to the screen, no show.
Yeah, right here.
Thank you.
Yeah.